Thank you, Professor, for the time. My name is Ryan Julio as the representative of Team 2 with Wang Li and also Bom Sok Cha. And I would like to present our weekly progress about fabrication of piezo-resistive pressure sensors using a metal strain gauge. The first one will be the experimental conditions characterizations of our pressure sensors. So we will do experimental pressure measurement with the pressure gauge. And in here we have the syringe pump. In here we have the 150 milli, two syringes. And then the second one is the pressure gauge. And then the third one will be the connecting tubing. And then the thing that we can see in here that if we push or infuse the syringe around 10 milli, we can have around 6 kilopascal. And by this calculation, we can have the range, the pressure that we can apply through these syringes. And then based on this calculation, we can have the pressure range around 0 to 45 kilopascal. And then why is it important? Because in our numerical analysis result on the right figure, bottom, we can see the relationship between the stress, pressure sensor thickness, and also the pressure. And we can see that the maximum pressure load that we can have on our pressure sensor based on this analysis is around 50 kilopascal with the highest stress on it. And it means that if we are using this pressure setup, we can test our sensors perfectly. And then for the numerical analysis of pressure sensor design, so we want to uh, seek for the output voltage by the ratio of voltage of our pressure sensors. But before that, we have to calculate the strain analysis. So before we have determined that we have the maximum pressure of the 50 kilopascal. So based on this value, we are ranging the pressure that we want to apply to our pressure sensors. The first one is this 10 kilopascal, 30, and also 50. And we can have the strain value of each of the simulations. And then based on the theoretical analysis by the gauge factor and also strain relationship, we can have the relationship between the ratio of voltage out and also voltage in and also the pressure applied to our sensor. And we can see that the minimum one that we can apply is around 10 kilopascal, and we can have it's between around 0.5 voltage that can be read. And also, if we are put into the max, we can have in the range of 0.2 and to 0.5 ratio of voltage. And for the sensor characteristic, it's to explain more about how we can characterize our pressure sensors. So the first one, it's the pressure off. So we are not flowing the airflow through our sensor. There's no bending on the diaphragm of our sensors. And if we are applying the syringe pump, it means that the airflow will be flowing into our pressures and also the load will causing the diaphragm to bend, and based on the resistivity difference because of this bending, the field will be different. So we can have the readings of our pressure sensors voltage. And then for the sensor characteristic, so if we have our design photo mask, we can see that we will apply four resistance, and the value of the resistance 1 will be the same as resistance 2, and also the resistance 3 will be the same as resistance 4. And then for if there is no like pressure applied, it means that the value will be the same for R1, R2, and R3 and R4. But if we're applying the airflow, it means that there's like pressure applied, and then this value will be different. And then by this differentiation of the resistivity by the Western bridge, we can have the delta R, and also we can have the voltage ratio that can be read by our pressure sensors. Also, if we are correlated with the strain, we can also have our readings on the voltage ratio of our pressure sensors. For the experimental setups, we have the syringe pump to generate pressure, and then the second one will be the function generator, which produce electrical waveforms of different shapes, frequencies, and amplitudes. Second one will be the amplifier to increase the power, voltage, or current of a signal. And then the third one will be the source meter, is to precise the voltage output display. And the fourth one will be the pressure sensor, which converting the syringe pump flow rate into a pressure value. And then for the step itself, how we can measure this characterization. So we will put the value on our syringe pump, and then the pressure will be generated, and then the diaphragm of our pressure sensor will be uh, bent under a load, and then based on the difference resistivity, based on the diaphragm curvature, it has voltage read by the function generator, and then we can increase the signal by the amplifier, and then the last step will be the read of the final voltage by the source meter. Next will be the mask design. So we have decided to put four mask design. The first one is the mask one for open window. The second one is the center pattern. The third one will be the backside etching, and the fourth one is the sensor pattern, which we want to test of each of our resistance value. For the fabrication process, we have done the first step of our fabrication process, which is the wafer oxidations. So we were utilizing the thermal oxidation of furnace, and the process it's we are heating up the silicon wafer up to the 400 degrees Celsius by 5 minutes Celsius per minute with the nitrogen, and then we will increase the temperature up to 800 and also by the 1000 degrees Celsius, and then we will oxidize it for 40 minutes with the nitrogen, and then we will cool down the silicon wafer. And then for our pressure sensor itself, we are targeting the thickness of this oxidation layer of 300 nanometers. And and then to measure the thickness of silicon dioxide layer, we can see that from the left picture, before the oxidations, there is no color on the surface, and then after the oxidations, the silicon wafer has some kind of vibrating colors. And we can see that from the bottom picture, there's a correlation between the colors of the surface of the silicon wafers, where it has the dioxide layer. And after we matching the color intensity, we can determine that our layer is around 300 nanometers.